welcome to this explainer brought to you by Forge College. Okay, so today I'm stepping into the lab as your head engineer, and we are drafting a meticulous, completely bulletproof blueprint for comparing EVM and SVM cost models. Now, if you've been following along with us, you know we've already looked at operational controls and how to catch cost regressions. But today we're shifting gears. We're moving from just operational monitoring to rigorous, actual scientific comparison. We are setting the methodology and scope for our Capstone project, which means we're defining exactly how we will measure and compare these two very distinct environments.
Okay, let's dive into this, because let's be real, anyone who has spent even 5 minutes in the Web3 space knows that comparing Ethereum's virtual machine to Solana's virtual machine is pretty much a guaranteed way to start an internet flame war. The crypto community has this really bad habit of using noisy, isolated anecdotes to just declare one chain the ultimate winner, rather than relying on, reproducible science. Think about it. If our methodology isn't flawless, our results are just going to be another loud opinion shouting into the void. So how do we actually do this fairly?
Well, think of our agenda today as a technical patent schematic. First, we'll navigate the apples to oranges trap. Then we'll establish a production line analogy, map out a concrete 6-step blueprint, test that out with a token transfer example, and finally sign off on what we call the reproducibility contract. Let's get right to it. Starting with Section 1, the apples to oranges trap, or how we go about busting bad benchmarks. So the absolute most common mistake engineers make here is comparing a single cold start EVM execution, where the caches are completely empty and the state hasn't been accessed recently, against a totally warmed up SVM runtime. Guys, that is a fundamentally invalid apples to oranges comparison. It just doesn't work. If you fail to control for massive variables like account warm-up state, load distribution, or your RPC client batching, your data is compromised from literally the very first run. We absolutely have to ensure we're comparing equivalent states under equivalent conditions. Otherwise, the numbers are totally meaningless.
Moving on to Section 2, the production line analogy, which gives us actionable cost accounting.
And this brilliantly illustrates the core concept. I want you to imagine every single transaction as a physical product moving down a factory assembly line. As it moves, it passes through different stations, things like CPU cycles, memory access, I/O, or a syscall. And every single time the product passes a station, that station charges a fee. This metaphor is super powerful because it forces us to separate our measurements into 3 distinct, highly measurable layers: the station, the product, and the overall factory throughput. Let's zoom in on that first layer, the station-level cost, our per-op metric. This is the absolute smallest billable unit we can possibly measure. On the EVM side, a station might be a storage read, like an S-load operation, and that's measured in gas consumed. Over on the SVM side, the equivalent station would be a runtime compute instruction, measured in build compute units. We have to explicitly define both the logical name of that atomic operation and the exact mechanism we're using to measure it. Trust me, mixing different atomic units when computing your averages is just a recipe for disaster. Now, zooming out one level, we get the full product cost. This is the cost of a single, complete transaction execution. But here's the catch. Raw gas or compute? That is not the whole story. To make sure both the numerator and the denominator match perfectly across both chains, your per-transaction cost has to include everything. We're talking raw gas and compute for sure, but also validator fees, the RPC relay overhead, and any application layer retries from that first attempt all the way to final confirmation. All of that makes up your true per-transaction cost. Finally, we look at the factory throughput cost. This translates to our per-user or per-session view. It takes those realistic user journeys, translates them into workload mixes, and samples them over a longer period, say 30 days. Ultimately, this aggregated cost per user is the bottom-line metric that stakeholders actually care about when they're making major architectural decisions. It's the big picture of our entire factory. All right, Section 3, the 6-step blueprint for a repeatable methodology. Let's see how this builds. To turn your research into reproducible science, you just follow this exact, literal schematic. Step 1, define your scope and goals. 2, pick your app. 3, design the benchmark with strict control variables. 4, instrument your data sources. 5, execute randomized runs. And 6, analyze and document. It's a structured pipeline that completely takes the guesswork out of the equation. I really want to zoom in quickly on step 4 here, instrumentation. You need comprehensive data collection directly at the station boundary if you want to reconcile all your totals later on. You've got to combine on-chain transaction receipts for your gas and compute totals with node-level metrics like CPU and memory usage. Add to that your client-side traces for timestamps and retry counts, and finally, deployment metadata like specific build IDs or commit hashes. The whole shebang must be captured and linked.
Next up, Section 4, the token transfer example, where we run a test batch.
Imagine we're testing a native token transfer loop that drives, say, 80% of an app's traffic. Think of this grid as your engineer's clipboard. Notice the strict discipline required here for benchmark design. We hold certain variables absolutely constant. Those are our control variables. We pin the client library to a specific commit hash, we ensure the account state is warmed up uniformly, and we use the exact same type of RPC endpoint. The only thing we change, our varying variable, is the concurrency, testing sequential runs against 10x or maybe 100x parallel requests. Once you run those tests, and by the way, you need to do at least 30 repetitions for a proper statistical sample, we have to apply strict statistical discipline to the analysis. Do not, I repeat, do not rely solely on single run values to make your claims. A single run is literally just an anecdote. You absolutely must record the arithmetic means and the 95% confidence intervals. If you're going to stand there and claim a deterministic advantage for one chain over another, you have to report the actual effect sizes. And that brings us to Section 5, the reproducibility contract, our final sign-off. Listen, a methodology is only valid if another engineer can blindly follow your schematic and get the exact same results. No exceptions. Your Capstone plan isn't just some document. It is a reproducibility contract. Your final deliverable has to include a checklist containing exact terminal commands, all environment details and variables, precise storage locations for your raw datasets, and small sanity check validation scripts to make sure the metrics are exactly what we expect. So, the crucial point is this. Reconciling your sums is the core audit that separates careful analysis from noisy anecdotes. When someone else runs your reproducible test, the per-op totals must perfectly add up to the final product cost. If the sum of your individual station fees does not equal the per-transaction cost, well, you've got unaccounted overhead or a missing measurement somewhere. That beautiful mathematical harmony, that's what actually validates your entire framework. I'll leave you with this final provocative thought as you gear up for your own benchmarking phase. Look closely at your methodology and ask yourself, is your benchmarking a rigorous scientific proof, or is it just another loud opinion waiting to be debunked? That is exactly what this capstone framing is all about. I highly encourage you to visit forge.college to dive deeper into the subject and explore more foundational Web3 engineering resources. Thanks so much for joining me in the lab today, and I'll see you in the next explainer.